My name again is Hassan Aoude. I'm a professor at the University of Ottawa. So our first presenter couldn't attend today, so this is a backup presentation that I presented at a previous ACI session, but it's related to what we're going to cover today, which is UHPC columns. Okay? So this was done a few years ago. So this project was done in collaboration between my university and McGill University, which was where I did my PhD, with Professor Dennis Mitchell at McGill. Okay, so let's go. So I'll just go over the research program. So the tests, we're looking at the axial performance of large-scale UHPC columns detailed according to code requirements. At the time, there was some tests on UHPC columns, but many on small-scale size. So we tried to do some larger-scale tests at that time. I know Mohammed is going to show some really large columns later, but this was the goal, was to see what's the effect of tie spacing, tie arrangement, and compare UHPC to HSC columns. So in the program, we had 6 UHPC columns. They had a height of 1 meter. The section was 250 by 250 millimeter, and we had a very small cover of 10 millimeter. The variables we had, you can see the cross sections which are shown here. We had 2 different cross sections with 2 different tie arrangements. So we had the first one, which is shown on the left, and the second one, which was shown on the right. So we call that C3 because there's 3 legs of transverse reinforcement, and C4 because in the second one because there's 4 legs of transverse reinforcement. And in the spacing, we went from 120 millimeter to 40 millimeter. Okay, you could think about that like conventionally constructed column to a seismically detailed column at the extreme. The UHPC we use, there's many different proprietary UHPCs. This is the one we use. It's CRC, Compact Reinforced Composite. This is out of Europe, in Denmark. It has a compressive strength of about 140 MPa. It has 2.5% of fibers by volume of concrete. The fibers are similar to standard fibers, 13 millimeter long. The aspect ratio was 43, and they were brass coated and high strength fibers, about 3,000 MPa. You can see here the fibers on the left. That's the slump flow that we did for the test. At that time, there wasn't UHPC specifications for flow test, so we did a standard SCC type slump flow test. And you can see it has quite a bit of flowability, although it's quite viscous and difficult to place. All right. So here's the compressive behavior of the UHPC. You can see you get about 140 MPa. And what's interesting, you do get some post-peak behavior. It doesn't just explode on once you reach the peak. And it has some good flexural and tension behavior. Okay, this is the steel. We use standard 400 MPa steel. The launch tool reinforcement were 15 M bars, so 16 millimeter diameter, like the number 5 bar that you have in the US. And the transverse reinforcement was 10 M bars. These are slightly larger than the number 3 bars. And grade 400 MPa, which is the standard steel type that you're using in Canada and the US. Just as a note, we did this in Canada, so that's why I'm using the SI units. So we used the CSA standard. At that time it was a CSA standard 2014 edition. We had 3 different detailing requirements, kind of like what you have in the ACI. RD of 1.5, this is the ductility ratio, this is conventional construction. This is just like your typical detailing that you have without considering seismic effects. RD 2.5 is our moderately ductile columns. And the third one, RD of 4, this is our ductile columns. Okay? Mohammed can tell you the names that you use in the US, but kind of the same idea. We have very similar requirements. Okay? This is just the test matrix. So again, the first number is the tie configuration, C3 when you have 3 legs of ties, C4 when you have the 4 legs of ties. And then the second number you see is the tie spacing, which as I said varies between 40 and 120 millimeter. So it's cutting off here on the screen. But this is what kind of looks like. This is the C3 series. You can see the different tie spacings. So starting from S equals 120, which is very large tie spacing, S equals 80, S equals 60 millimeter, and S equals 40 millimeter. So that 40 millimeter is kind of like your seismic design that you currently have. And then in the C4 series, because we have more transverse steel in the section, we can kind of increase the spacing. So we started with 120 millimeter to be able to compare the effect of tie configuration. And S equals 60 millimeter, that's kind of your seismic design. Again, you can have a larger spacing because you have more transverse reinforcement in section. Okay, so First thing you can see, these are the moderately ductile columns. This was to compare the tie configuration, these two specimens. Sorry, it's cutting off there, I don't know why. These are the ductile columns with 40 millimeter or 60 millimeter spacing. And then in each series we had these different spacings just to look at the effect of the spacing itself. Okay? And then within each series we have some columns with the exact same spacing, so with different configurations, so we can look at the effect of configuration like C360 and C460. We can look at the same spacing but different reinforcement arrangement, transverse reinforcement arrangement. Okay, these are what the columns look like. You can see quite a bit of steel for the seismically detailed column and less for the non-seismic on the right. Okay, this was the section in the formwork. As I said, we had a very small cover of 10 millimeter. That's just because of the capacity of our testing machine. We tried to focus more on the core behavior. And you can see it there. And we cast them upright, as you can see. This is the pre-mix UHPC. It's just a mortar where you add water and the fibers, and we use the standard mixer here. We had quite a bit of trouble with that. You can have now pan mixers, which will give you better results for mixing, but we were able to do it with this mixer that's shown there. Okay, so here are the steps for the casting. We put the dry mix, add the water, add the fibers, and then you placed it as shown there, and then we did our standard tests. Okay. We tested them with the 11.4 meganewton MTS machine at McGill University. You can see the column there. This is the student doing the test. The setup is as shown there. We had some steel collars at the ends just to prevent failure at the ends. And then we had axial load measured by the machine. And then the displacement, axial displacement, was measured by 4 LVDTs, taking the average of that. Okay, let's go over the results. Okay, I'm just going to talk about different things here. We're going to compare mostly the load strain response, but you can compare also the peak load, the peak strain, normalized load, the strain at 85% dropping capacity. That gives you an indication of ductility. And we also took the area under the curve up to 0.002 strain, again to give an indication of ductility. Okay, so these are just a table of the results. This is the C3 series. You can see with different tie spacings. You can see as you reduce the tie spacing, you get a larger axial load, as shown in the Pmax column. You can also see you get more maximum strain, you get more ductility, and so on. So the performance does improve when you reduce the tie spacing. Also, as we'll see, it does improve when you improve the tie configuration. So these are some typical results. So you have the axial load versus the axial strain. Strain is just that axial displacement divided by the displacement gauge length. So we can see the different curves here. The black curve is your standard, normally detailed UHPC column with large tie spacing of 120 millimeter. You reach an axial load of about 8,500, 9,000 kilonewton. And then you can see when you start to reduce that tie spacing, the performance improves. You see two things, an increase in axial capacity, and you can see quite evident an improvement in the ductility. Okay, just as a note, that was the MTS capacity of the machine, so we got there. That's why you don't see many of these large-scale tests, because you need huge capacity machines to do these tests. Okay, this is the second series now with the C4 arrangement. Again, same sort of trend. The blue curve is the 120 millimeter spacing. The red curve is the one with the closely spaced ties. Again, you can see an increase in capacity and an improvement in the post-peak response. Okay, and this is just showing the same thing. This is just 40 millimeter versus 120 millimeter. You can see all the parameters are improving. So axial load capacity, maximum strain, the ductility strain, the toughness, which is the area under the curve. You can see 145 versus 87. Those are numbers, but you can see there is quite a bit of improvement in the ductility as you reduce the tie spacing. These are just strain readings on the transverse reinforcement. I'm trying to remember what I had here. But you can see with the column with the closely spaced ties, you can see the transverse reinforcement is engaged. So it is working. You can see there's quite a bit of reading there on the transverse reinforcement. Okay, so now we're just comparing the configuration. So we're taking columns with same spacing, but different configuration. So C3 120, that's the one with the 3 legs of transverse reinforcement. C4 120 was the 4 legs, but now you have quite large spacing, right? 120 millimeter. So you can see there is an improvement with the C4 column, but because you're getting buckling of the bars and other things, right, it's not doing that much of an effect. Okay, so quite similar actually, the responses. This is now with the closer tie spacing. So now you're limiting buckling because your tie spacing is less. It's 60 millimeter now. Now you can see when you use this C460 configuration compared to the C360, you can see some improvement in terms of load and the post-peak response. Okay, and these are just some numbers. Okay. These are 2 columns detailing with the same requirements in the CSA standard, right? The seismic detailing requirements. We have the C340, which has a 40 millimeter spacing, and the C460, which has a 60 millimeter spacing, but they have the same kind of code requirements that we're following. You can see that responses are quite similar. So you can play with the spacing of the transverse reinforcement and the configuration of the reinforcement to get the response you need. This is just very interesting because if you've tested these or looked at these high-strength concrete columns, when they fail, they explode, right? Very brittle, especially the cover is very brittle. This is the failure of one of the columns. You can see how it fails because you have the fibers in there. Although you have ultra-high strength, you can see the cover gradually spalls, right? So very different, distinct behavior when you compare it to regular high-strength concrete. Okay? This is something we did notice. You do get buckling of the reinforcement, so you can see the buckling is taking place here. And actually what happens is that cover starts to kind of weaken. The bars buckle and push that cover out. You did see the buckling. But as you go to the low tie spacing, then the buckling is almost not there. And you can see here the confinement, right? This is after failure in the C340 column in the right side curve figure. You can see not much damage at all. And this is just what I was mentioning, the buckling of the bars pushing against the cover of the UHPC. Okay, and this again just showing that process of spalling is quite gradual. All right, I don't know how much time I've left here. So we did compare to some high-strength concrete columns that were tested by Professor Murat Saçoglu at my university, at University of Ottawa in 1999. Same exact column, detailing, same size, but with regular high-strength concrete. Okay, this is just an excerpt I took out from the student's thesis. And you can see they mentioned the sudden loss of strength was observed in these columns immediately after the peak load, and they mentioned it suffered early spalling of cover concrete. So you can see that here in the photo that I asked Professor Murat to give me. You can see the cover spalling. So, and this is just comparing the behavior in terms of normalized load. You can see the UHPC column versus the HSC column in dashed. You can see the improvement there. These are normalized curves. And again here for another one. Okay, so I'll skip the analytical modeling because I've been speaking quite a bit. So we did model these and we just used some compression model for the UHPC, confinement models for the core concrete, and a bar buckling model, and we were able to get quite good response there. Okay, so these are the conclusions. We saw that by reducing the tie spacings in the UHPC columns, we improved the confinement, leading to increased strength and ductility. When we improved the detailing of the transverse steel within the cross-section, we further enhanced the confinement. We saw that fibers in the UHPC allow for gradual and controlled cover spalling. And when you combine fibers and closely spaced ties, you can get controlled failure of core concrete. The axial load behavior of UHPC columns is improved when compared to HSC columns. And we mentioned that we can get reasonably good analysis results just by doing sectional analysis and including a model for the UHPC, core concrete, and the launch tool reinforcement. So that was my presentation.